presentation. Next speaker is Dr. Peter Irwin from Rowan, Williams, Davis, and Irwin, Inc. Topic to present is a guideline for wind tunnel testing of tall buildings. Dr. Irwin has undertaken research in wind engineering and been involved in wind consulting for over 35 years. He's a principal of RWDI since 1980. From 1999 to 2008, he served as chairman of RWDI and is actively involved in the wind engineering of major structures with special interest in tall buildings.
Well, thank you very much for that introduction. This guideline came out of a meeting in New York a couple of years ago where myself, Roy DeNoon, and David Scott were poring over wind tunnel results from our laboratory, from CPP, and of course David Scott was the structural engineer, and we were trying to resolve differences between the wind tunnel results. And it occurred to us during that meeting that this process would be a whole lot easier if we had certain standard methods of presenting results. And also, David had a number of issues which he thought needed to be brought forward about wind tunnel testing and how it relates to building codes and how sometimes the process of wind tunnel testing involves maybe a much more in-depth analysis of something like the wind climate than may have been done for the original code. This depends where you are in the world. And so this kind of information should be made available. Anyway, we committed ourselves to writing a guideline under a rather overly ambitious schedule at the time. And we're about a year behind schedule, to be honest. But we do have, I think, at least yesterday, at the beginning of our meeting of the working group, we had 6 of us sitting there. I thought we were about 95% complete towards the first draft. By the end of the meeting, I realized we were probably only 85% complete, which is probably a good thing. It meant that we had a lot of useful input coming from the meeting. Well, let's get into the process for completing this guideline. We did begin work back a couple of years ago in 2009, and the authors of this first draft are the 3 of us who were at that meeting. It's now about 85% complete, and I think we're getting close to the point where we want to circulate it to a well-qualified review committee. And here we're thinking that the committee would be made up of a variety of people who are active in tall buildings. So we'd have architects, structural engineers, wind consultants, and we may try and broaden it to somebody from the development or construction management point of view as well. Anyway, we have a list of about 20 names which we went through yesterday. I'm not going to lay out who those are at the moment, but we would hope also, besides getting a variety of backgrounds on the committee, but also have some good geographic distribution from different countries and different parts of the world. So we would circulate this first draft and I think give the review committee a month or 2 to review it, get their comments back to us, and then we would incorporate the feedback and hopefully produce a final manuscript. If the feedback shows that we've got a long ways to go, then we probably have a second round of feedback before doing the final manuscript. Well, what are the objectives? Well, first of all, it's to provide a wind tunnel testing, or a guide to wind tunnel testing for for tall building designers, not so much for the wind specialists, but for the designers. Wind engineering is a specialized field with fairly complex concepts and also its own sort of technical jargon, and one can't expect generalists or designers to know all of this. And wind specialists who are knowledgeable in the field already have some standards that they can go by, such as the ASC practice note published in 1999. Here in Korea there's a design guide for wind effects. There's an Australian guide, and I understand there's also a guide in Japan. Also, another objective would be to promote good practice amongst wind tunnel test laboratories. And coming from our original meeting, to facilitate comparison of results from different wind consultants when they're doing peer reviews. So the main sections would be an executive summary, introduction, and we have to start with the wind climate for reasons I'll talk about a little later. We have to have an educational section, I think, on the nature of wind loading, which puts the rest of the standard in context. So we'll discuss things like vortex shedding and the different types of wind loading that you can get. Then there'll be a section on the different types of wind tunnel test methods, again written in more layman's language to provide architects and engineers and developers with enough background to understand what they should be looking for when they want a wind tunnel test. And then there's the process of going from the wind tunnel results to the final full-scale predictions, which are in the form of loads for strength and serviceability. We need a section on quality assurance, and then there's one section specifically devoted to this format for comparing wind tunnel results. And I think also one of our decisions yesterday, which isn't reflected in this slide, is to add a standard CTBUH specification for wind tunnel tests, which might be useful to structural engineers and architects. And finally, there'd be a section on how to interpret wind tunnel results. And of course, there'll be references and maybe a couple of appendices. But I think we have 8 out of the 9 sections written in first draft form, which still need to be polished. And we have yet to put it into an executive summary, but we're getting very close. So the introduction, I'll just go through some of the sections here, will be a description of why one does a wind tunnel test. Essentially, it's because to use building codes can be a process that doesn't give you the accuracy that you really need on a tall building. Building codes are written for the majority of buildings, and tall buildings are a much smaller fraction of the population and require a lot more complexity in the type of study that needs to be done. This guideline, it'll explain the reasons that I've been talking about as to why we need the guideline. It will caution the design community about mixing the analytical methods of codes and standards with wind tunnel methods. And I'll get into that a little bit later. In fact, the next bullet point really is a way of illustrating why we shouldn't do that. It's to do with the Davenport chain. Alan Davenport was a famous researcher that many of us know, who unfortunately passed away a couple of years ago. But he conceptualized wind loading as a chain, and as with any chain, if there's one weak link, then the chain is only as strong as the weakest link. So it's important that all the various links in the chain are dealt with due diligence. It'll also comment on the use of code design speeds. There are some parts of the world where tall buildings are relatively new, and the building code wind speeds may not have been developed with a lot of effort put into them, because frankly many buildings are not that sensitive to wind speeds, and so there may not have been any reason to really look at the wind speed that closely. But when you build a tall building, it's extremely important to have the best accuracy possible on design wind speed. Let's come back to this Davenport chain of wind loading, and it's got 5 links. First of all, the wind climate needs to be thoroughly understood, because tall buildings have a response which is extremely sensitive both to wind speed and wind direction. If there's uncertainty in those, then it will be magnified in the wind loads. If you have a crosswind response, which depends on wind speed to the power of 4, which you sometimes see when you have vortex excitation, and you don't know the wind speed to better than 10%, then you've got uncertainties of 40%. So that's just an illustration. Likewise, the wind direction is also important. Then there's the influence of terrain. That's more or less the exposure that you use in building codes, open and built-up exposures, for example. And then you have the local aerodynamic effects, which depend on the building's shape and on its immediate surroundings. Other buildings around a building can have a dramatic impact on its loads. And then the next link is the building dynamic effects, which depend on its natural modes of vibration, its mass, and its damping. And then finally, you bring all that together, and the final link is combining the results from the central 3 links with the original wind climate statistics to come up with predictions of design loads for given recurrence intervals, or accelerations for various recurrence intervals. So this kind of conceptualization is going to be in the standard, at least in this guideline, and it actually, as we'll see later, forms a useful way of checking wind tunnel studies at various points through this process. So there is a section then on the nature of wind loading, so it'll describe the concepts like the planetary boundary layer, mean and fluctuating loads, what we mean by long wind, crosswind, torsional loads, the background and resonant responses, vortex excitation, aerodynamic damping and galloping, cladding loads, and we should at least touch on Reynolds number effects as well. So these concepts will be familiar to many of you with the wind profile or the wind velocity profile explained, along with its turbulence that's in the oncoming wind. And then also we have the building's own signature turbulence that comes off it, which causes vortex excitation. We'll explain the general flow patterns that you typically see around buildings, which allows you to get a feel for why, for instance, you have those highly accelerated flow zones down at the bottom of the building, which cause problems for pedestrians, and why you have a stagnation point high up on the front face of the building. And phenomena such as corner vortices, which give rise to high suctions on cladding, and also they can cause problems on roofs. We just have been involved recently on a building that had a roof area on the 50th story and had 95-pound concrete pavers lifted off during a windstorm. caused by those vortices. Also, the concept of the background response and the resonant response is explained, since those are important. And the way vortex shedding influences the response of the building in the crosswind direction as a function of wind velocity. Now, the key points when we're comparing results of wind tunnel testing need to be explained. So when you have a complex problem, is really the way you can get somewhere in solving the problem is to break it down into its component parts, and then they become easier. So this principle is used here. So we'd break the wind studies down into components of basically based on the Davenport chain. And then you can compare each link and see if differences occur at that link. So you'd start off by comparing wind climate statistics. Then you need to compare the effect of the terrain, which means the wind profiles in the wind tunnel. And then you compare the aerodynamic measurements made in the wind tunnel. And these need to be expressed in a readily comparable form. And that form is non-dimensional aerodynamic force and moment coefficients. And likewise, when we're looking at the spectrum of loading on the building, those spectra need to be in a non-dimensional form, so that literally you could take the spectrum plot from one laboratory, sort of lay it right over the top of the other laboratory, and those two curves should lie right on top of each other. And then finally, you need to compare the responses at different recurrence intervals, and that brings in the wind statistics and the directionality effects. My experience is that this last step and the first step of comparing wind climate statistics, that's usually where the big differences arise. And so this really brings the Davenport chain in again. The first link, you compare wind speed versus return period and directionality plots. The next link is where you compare the boundary layer profiles and reference wind speeds. When you're in the wind tunnel, you have to measure the wind speed at some point in the working section, and that then is your reference wind speed. Some wind tunnel laboratories use a different location, and as long as we know where it is and know the wind profiles, you can relate the results. But that has to be known and has to be presented in the report, in the wind tunnel report. And then you compare the aerodynamic effects, which is in these non-dimensional force and moment coefficients. And I'll give some examples of that. And then after you've included the dynamic effects of the building, its natural frequencies, the damping and the mass, you can work out the expected peak responses of the building for various wind speeds and wind directions. Regardless of what the wind climate statistics are, you can make a prediction just based purely on the wind tunnel for any given speed and wind direction as to what the full-scale response should be. And that should be comparable directly between the wind tunnel labs. And then finally, when you bring in the wind statistics combined with the information from link number 4, you do a final check of the results at link number 5. My experience has been that when peer review has been done, people have gone straight to link number 5, found differences, and then you spend a lot of time going back trying to find where that originated from. So there'll be some examples of typical presentations that the wind statistics could be presented in. Normally there would be at least a plot of wind speed versus return period, such as in the left-hand plot. And then there needs to be another plot showing the directionality. The example plot here shows the probability of the 50-year wind speed being exceeded for each direction. Then we go to the wind tunnel and we simulate it using roughness on the floor and spires at the working section entrance, and maybe a trip as shown here to trip the boundary layer. Whatever method is used to produce it, in the end you should have profiles of mean velocity and turbulence intensity, like on the left and right hand side here, that should be comparable for each of the upwind fetches that you're modeling. Now the model in many cases would involve pressure tapping, and so here is an example of a pressure tapped model, not of a particularly tall building, but there are many hundreds of buildings or wind tunnel tested that are not super tall, but they do undergo the pressure test. And these pressure measurements can also be used to obtain structural loads. If we do a pressure test, normally these are the kinds of presentations you would expect to see. The one on the left shows a building elevation, just one of the 4 elevations with the locations of pressure taps shown. And then over on the right-hand side is a contour plot resulting from the prediction from the wind tunnel of 50-year pressures. Normally the contour plot is, well, often it's omitted, and you would finish up with a block diagram plot like this. We'll also describe high-frequency force balance testing, aeroelastic testing, such as this model of Burj Khalifa with a central spine and different shell components on the outside. And so having described the different types of tests, then there'll be, this is a definition of the force and moment coefficients. And these are in non-dimensional form, and I emphasize that because it does allow one to do direct comparisons between the labs, even if they tested with different scale models, different wind speed ranges in the wind tunnel. As long as we can get back to these non-dimensional coefficients, they'll be comparable, and they can be plotted versus wind direction. These are the mean and root mean square of fluctuations of the base moments and base shears. Similarly, the power spectra for long wind and crosswind can be compared, and in non-dimensional form. And then this is an example of a presentation of the peak responses after including the dynamic effects. And then finally, we combine that information with the meteorological data, or the wind statistics, by several methods. Now, the simplest method is the so-called non-directional method, whereby you assume that the 50 or 100-year wind speed blows from all directions. So you sort of take your worst case coefficients, and those will be the highest loads. But that penalizes the design of tall buildings hugely, and it would make them very uneconomical. So the state of the art is to use a directional method, and there are 3 different methods outlined in the guideline: the sector method, the extreme load effect method, and the upcrossing method. And here's an example of those, say, base moments predicted by, in this case, the upcrossing method, and the directionality factor. In other words, the reduction that was caused by taking into account wind directionality is given by those factors. So you've got typically about a 20% reduction due to the directionality, and it's good to identify that clearly in the wind tunnel report. And another type of presentation is to present In this case, accelerations as a function of return period, and compare it with criteria. Well, that brings me to the end of this talk, and we will be looking for interested parties who would like to review this guideline. So anyone who is interested, they could contact myself or David Scott or Roy Denoon, and we'd be pleased to put your name into the pot when we're trying to decide on a review committee. Thank you very much.